So the correlation coefficient is a measure of how associated two values are. There's a very closely related technique known as regression, which helps you assess statistically whether those measurements are associated, and also quantifies the relationship between the measurements. So what regression aims to do is fit a straight line, the best straight line possible, through the data. It aims to sort of minimize the distances of the data overall to that straight line. I won't go into the details of how it's fitted, but it comes up with what it thinks is the best straight line, and the line can be defined by an equation that looks a bit like this. So you've got the y-axis is equal to a constant, which I've called a, and that'll be the sort of value where the line hits 0, so about 5 and a bit. And then it's plus a slope, which is a number, which is the b constant, multiplied by the x value. So the larger b is, then the steeper this slope's going to be. And then you have an error term, because the slope doesn't exactly predict the data, they're all going to have a bit of an error about that slope. And so regression can be used to answer a few different questions, and depending on what you want out of your data. You might want to simply say, is there a significant positive or negative slope? So that's really saying, have I got significant correlation between my two values? And it will come up with a p-value to test that hypothesis. It quantifies how related white blood cell counts and platelets are, because it gives you this slope, and also you can get the correlation coefficient from it. It might be that you want to know, can white blood cell count be predicted from platelets? And you've now got an equation that you could, if you wanted to, use to try and predict white blood cell count if you'd measured platelets but you hadn't measured white blood cell count. It's probably very unlikely you'd want to do that, but it does allow for that as an option. So in our case, our equation looked like this. We're trying to fit a line to give us white blood cell count, which is on our y-axis, and we find that the value of A was 5.23, so it's this value here at 0, and the slope was quite small. Note the slope isn't the correlation coefficient, and it's very dependent on the scale of the data. So because platelets is on much bigger scale, it's not surprising that this value for the slope is quite small. So that sort of forms the equation, the regression equation, to predict white blood cell count from platelets. Usually the values of A and B, that's called the intercept, and the slope are not of particular interest though. But we could, if we wanted to, use this to predict white blood cell count from platelets. So to show an example of some statistical output from a package, this is the Minitab output. So it gives you various things. It gives this, and it probably takes a little while to work out what it's giving you, but in fact this table, the COF column, which it doesn't really explain properly, but that's that constant term, the A term, and we've got the slope for platelets. But what we're quite interested in is this p-value, and that's testing whether the slope is significantly different from 0. And it annoyingly gives us a value of exactly 0, which I think is really effectively less than 0.00001. And that's saying that yes, we have got a significant slope. We're sure that slope is positive, and if we did this study again, we'd get a positive slope. Maybe not exactly that value, but we'd get a positive slope again. So that's quite a useful result. It's proved that white blood cell count is correlated with platelets in this study. You can really ignore these values. The only thing to note here, these are used in calculating the regression equation, but the only thing that might be interesting to note is this R squared is a measure of the variation in white blood cell count, which is accounted for by the slope, i.e. the platelets, and that's 31.8%. And if you were to take the square root of that 31.8%, you would come up with the correlation coefficient of 0.56, which is just what we had before when we just looked at the correlation coefficient. So it's useful to see that really regression and correlation analysis are all the same thing, really. Gives us results a bit differently in terms of this analysis of variance table. I'd probably ignore this because you don't need it. The p-value will be exactly the same as the p-value up there, calculated using a slightly different test, but it's effectively equivalent. So in terms of Minitab, I don't think you need to look at that table.